So if you've looked at the video for section 1.2, you'll know that we're talking about correlation. And if you haven't looked at that video, hopefully you've looked through section 1.2, because section 1.3 leads straight on. We've got these idea of these graphs: strong negative, strong positive, weak negative. So I'm not going to recap that. If you are not familiar with section 1.2, then, oh, excuse me, there's the clock striking. If you're not familiar with section 1.2, then have a look at that before you look at this video here. Now, what we've got in section 1.2 is we have this thing that we're calling R, and we're calling it the product moment correlation coefficient. And R could come out with a value of, let's say, 0.9. We put the data in our calculator, we say R equals 0.9, and we'd say, great, that's a strong positive correlation. We could say R is 0.02, and we'd say, fine, that is close enough to 0, that is no correlation. Now, the problem is, what if we're somewhere in between? What if R equals 0.4? What if R equals 0.6? Are we going to say this is a positive correlation? Certainly it's positive. Does it count as a strong positive? Does it count as a weak positive? What counts? Okay, how big does this correlation coefficient have to be before we say we have a correlation? Now, if you think about it and think back to last year's book, this is starting to be a familiar question. So the question that we were asking last year at one point was, if you flip a coin 100 times, how many heads would you expect to get? And we'd all say, well, we'd expect to get 50 heads. And then we'd say, okay, what if we got 53 heads? Do you think that's a biased coin? What if I got 57 heads? Do you think that's a biased coin? What if I got 60? What if I got 62? At what point do you say that's enough? That's the number which I'm going to say shows me this coin is biased. That's the number which I'm going to be happy with and say I'll be convinced that it's a fair coin. It's the same situation here. The product moment correlation coefficient could be 0. I can have 0 correlation. What if it was 0.1? Would that be enough to say that there is a correlation between these two variables? What if it was 0.2, 0.3, and so on? So what we have here is a situation where we're looking at a hypothesis test, isn't it? So the way it will work is this. If we have a set of bivariate data, so x values and y values, we can say, first of all, rho is 0. Now, this is where we've got to actually just stop a second and introduce a slightly different notation. We've got a rho and we've got an R, okay? Now, R is what we've been calculating. We've had our x data and our y data. Now, x data might be the weights of people. Let's say that we're looking at children and this is their weights, and y is we're looking at the heights of those children, and we'd expect a correlation between x and y, wouldn't we? Now, I could take information about 10 children, I could take their weight and their height, and I could calculate R, the product moment correlation coefficient for those 10 children, their weight and height correlated, okay? Now that would be the correlation coefficient for this sample that I've just taken. That's our R. Rho is slightly different. That is what's the correlation coefficient for all the children in the whole population. So if I'm looking at children in Britain, then rho is the correlation coefficient between the children, between height and weight for all children in Britain. And we would probably find that as height goes up, weight goes up as people are growing, okay? Now, can you see there's a slight difference between R and rho? It's quite possible that I take 10 children who don't follow the trend for some reason, okay? If I take a bigger sample, then I'm more likely to get a value of R which is close to the true value of the correlation coefficient in the whole population. The point is that rho is something which we can't really calculate. I can't take every child in the whole country and measure their height and weight. That mathematically is possible, practically it's not. So what I do is I take a sample and I calculate the correlation coefficient for the sample, and I'm going to hope that my correlation coefficient for the sample is similar to the correlation coefficient for the whole population. But because those things are different, I'm going to have R and rho as different notation for each of those things, okay? So let's come back to this hypothesis test. What we're interested in is our rho. We're going to say, well, first of all, I'm going to assume that whatever this data, this X and Y data, I'm going to assume that in the whole population there is no correlation. So my H0 is going to be rho equals 0. Now, if I'm doing a one-tailed test, remember that is, I suspect that rho is actually positive, that I expect there's going to be a positive correlation, or if I suspect there's going to be a negative correlation, then my alternative hypothesis would be rho is greater than 0. If I suspect there's going to be a negative correlation, my null hypothesis would be rho equals 0, there is no correlation. My alternative hypothesis would be rho is less than 0, there's going to be a negative correlation, okay? And the same thing with the two-tailed test. If you're familiar with hypothesis testing, you perhaps guessed this already, but here we go. If we think about a two-tailed test, we're not sure whether the correlation is going to be positive or negative, we just think there might be one. We'd say we'll start with the assumption that there is no correlation, and our alternative hypothesis H1 is that there is some correlation, i.e. rho is not equal to 0, okay? So, those are my hypotheses. What I then do is that I get my test statistic, and my test statistic is going to be my R, isn't it? That is going to be, I'm going to measure the data that I've got, I'm going to look for the correlation coefficient, and I'm going to see what number I get there, okay? Now, what I then need to do is compare R. So let's say R comes out as 0.6. Is that enough to say there is a correlation? Okay, now the answer is, it depends on the sample size. So it says, I think it's page 100, there we go, 192. So if you go to page 192, you get this sort of table. And the way it works is you look at the sample size. If we're working at the 5% significance level, we go for this column, and we almost always do, remember, but if you've got a two-tailed test and you're working at the 5% significance level, you have 2.5% on either side, so maybe we need this column a little bit. These columns here are only going to be very occasionally, almost every question is going to look at a one-tailed test and a two-tailed test at the 5% level, okay? So if I've got 4 pieces of data, I really need them to be in a good straight line before I can be convinced that there is any correlation. I've only got 4 pieces of data. So in that case, the significant value is 0.9. If my correlation coefficient, my R, is smaller than 0.9, I'm saying I'm going with H0. I'm not convinced there is a correlation. If my correlation coefficient R is bigger than 0.9, then I will reject H0, and I will say we have some evidence towards the fact, towards the idea that rho is not equal to 0 or rho is positive, okay? As the sample size gets bigger, and just picture this, right? If I've got 4 pieces of data like that, is that enough to show that that's a positive correlation? Doesn't seem very convincing. But as I add more points in, then I don't expect them to be really lining up exactly on a straight line, but as you can see here, that's a positive correlation, isn't it? It looks like there's a correlation. Those points are still not particularly close to our line, so I'm not going to expect an R particularly close to 1, but I'm still convinced that there is a correlation. And that's the question I'm asking, is there a correlation or not? So as the sample size gets bigger, the critical value here gets smaller, okay? So let's have a look at one particular example. There's a scientist taking 30 observations of the masses of 2 reactants in an experiment. She calculates the product moment correlation coefficient of minus 0.45. So that's definitely a negative number. Is it negative enough? Is it far enough away from 0 for us to be convinced that there is a correlation between these 2 reactants? The scientist believes there is no correlation between the masses of 2 reactants. Test at the 10% significance level, whether the scientists claim, stating a hypothesis clearly, okay? Now, the scientist believes there is no correlation, so there's no suspicion that the correlation should be positive or negative. So we're saying H0 is that the rho is 0, that these 2 reactants in general have no correlation between them. H1 is that the rho is not equal to 0. The sample size is 30. The significance level at each tail is 0.05. It asks for a 10% two-tail significance test. And this is perhaps a good point to say, I'm assuming that you remember the significance test from last year. I'm not going into detail on some of the, why this is 0.05 and given that we're on a 10% two-tail test. I'm assuming you know that from last year's work. So from the table, the critical value are for a 5% significance level with a sample size of 30. So you go down to the sample size 30 in here. you'd go across to 0.05 and you'd look up the value, and the value that you get is 0.3061. Now the value that we've got is further away from 0 than minus 0.3061, and therefore we are going to reject H0. There is evidence at the 10% significance level to show that there is significant evidence at the 10% significance level that there is correlation between these two things. And remember, when you're drawing those conclusions, again, I just point you back to the videos for the last time we did hypothesis testing on the last book. You have to be very careful about how you phrase these things. We can't say there is definitely correlation. We can say we have evidence to support the claim that there is correlation. We have enough evidence to reject the scientist's claim that there is no correlation. That's how we'd phrase it in this case. Although, if I'm honest, the exam board are a little bit, well, they're quite kind on what they will accept, at least on the mark scheme so far. As long as you get the idea that we're rejecting H0 and we're accepting H1, then they seem to be quite keen on giving you the marks, which is nice for us. Okay, so that's the idea. We work out our R. Is it big enough or big and negative enough? Is it far enough away from 0 for us to be convinced that there is some sort of correlation going on?